Okay, I think we could get started. It seems like there's a crowd, right? All right. So this is the second lecture of the gravitational wave data analysis triplet. The last one is going to be tomorrow afternoon. If you remember from the first lecture, we didn't really talk about gravitational waves at all, right? We just did some data analysis. We fit a line to data. This is the first time we're actually going to talk about gravitational waves. And we're not going to do any live fitting. I will do live gesturing at coding and then leave behind code for you to try offline. And the reason is we've gone from fitting a line to 50 data points to fitting a very complicated waveform, as we'll discuss in a minute, to hundreds of data points. And if I try to live code that, there's going to be too much time to fill. So I'm going to talk about how you would do it. I'm going to leave you a model, and then you guys can play with it. Okay? So what we're going to do, though, we're going to try to be real. We are going to try to talk about how we would fit 1509-14, so the September 14th, 2015 gravitational wave signal. And it's an ideal exercise for this sort of thing because you can see it in the data. None of the other gravitational waves that we've detected have been similarly strong in a raw time series. You have to do more processing to pluck the other gravitational waves out. So that'll let us get a little bit of feedback about whether our models seem realistic and what kind of values of parameters we might be expecting and so on. So let's do it. LIGO, by the way, so I'm not going to say that I am in complete agreement with LIGO's open data policy or any of the data policies that we have. But I will say that compared to your average Larry, Moe, and Curly in astronomy, we release a lot more data and are a lot more open. So I think we're probably a little lagging behind NASA missions where data becomes public and archived instantly, but we're pretty good. And one of the ways that we're pretty good is there is a LIGO LOSC, LIGO Open Science Center. That is where all of the data releases for all of the detected events happen. So right now, around each event, you can get a little over an hour, a binary hour, 4,096 seconds worth of data. And you can see I've got some links here in the notebook. LOSC, the LIGO Open Science Center. There's a nice tutorial page, and we're going to be following the BBH event tutorial, at least for the start of this lecture. I'd encourage you to click through. It's an IPython notebook. You download a few tens of megabytes, 100 megabytes, something worth of HDF5 files. It is the real strain data that we actually analyzed in LIGO. Okay, and it's fun. Yeah?
I didn't understand your argument. What makes you unhappy?
Oh, let's not. So, all of this makes me very happy.
That it's not as open as it should be? Or that it's too open?
No, I think that the collaboration is not as open as it could be to maximize scientific return. That's what I think in a very short phrase. And if you go out to dinner or lunch with me and fly me with alcohol, I will tell you much more.
That's what I'm doing tonight.
Yeah, that's right. Yes, okay. I will tell you much more.
But isn't the policy changing? Isn't it a thing that will, like next Science Run, is it going to get public faster?
I don't think I would say that. Alerts will get public faster.
Oh, okay.
We found something. Maybe.
We may have.
Yeah.
With
the false alarm rate and something on the sky, yeah, etc.
Yeah.
So if you have a telescope and you like to look at the sky, that will probably happen faster.
We're going from 2 years to 1.5.
Yeah, so I think the goal is, right now the goal is to, after 2 years, a full data release, not this hour around a detected event after we've written a paper 6 months later kind of thing, but a full data release. And we're trying to move that to 1.5 years.
I'm going to do correlated noise.
We are going to talk about correlated noise, actually. That's coming very soon. Though not the correlated noise you're thinking of. I might make a couple jokes, but otherwise.
Actually, the people here, we should invite them to your lecture. Maybe they can find out how LIGO analysis is done.
Yeah, that's okay. Well, it's too late now.
It means now, so.
That's true.
We should arrange a session.
Okay. Yeah, so you download some HDF5 files. There's some links here, and you download a Python library. You install some plotting software. You set up everything. You extract the data, and whoops, can't see it. There we go. That is a binary hour surrounding GW 150914. Isn't it beautiful? You can see it in the data. This is what LIGO data looks like. And the reason LIGO data looks like this is because at very low audio frequencies, say about 10 hertz, the Earth is ridiculously noisy. I don't mean noisy to your ears, but on the scale of gravitational waves, where we're talking about stretching and squeezing by a part in 10 to the 20 or less, the Earth is just rumbling along. Okay, you can hear the waves on the distant shore, you can hear traffic, you can hear logging, you can hear hurricanes, you can hear minor earthquakes, all of this stuff. In addition, if you squint at this, you can imagine, it sort of looks like there might be some periodic signals beating against each other in that data. So both because of unavoidable instrumental effects and also deliberate injection of sinusoidal signals, the LIGO data stream has a number of very high quality periodic oscillations, amplitudes in it. In particular, some of them, so I guess I should describe the LIGO instrument. Nobody's said what the LIGO instrument is. It's a Michelson interferometer. It's an L-shaped thing, 4 kilometers on each side. This is, when you've been in LIGO for a while, you can close your eyes and do stuff in your sleep. It's like 4 kilometers on each side. You send a laser into a beam splitter. Half of it goes down one arm, half of it goes down the other arm, and bounces around in a almost resonant cavity for a long time. Comes back out, gets recombined. And now the two different arms, the laser has made a measurement of the number of cycles that fit into 4,000 reflections between the cavity ends. On this arm and on this arm, when a gravitational wave comes through, the number of cycles is different in the two arms. And so rather than interfering destructively, you get a little bit of laser light out the dartboard. Okay, that's how an interferometer works. It makes it so the one sentence summary is it makes a differential measurement of the arm length. And a gravitational wave, which squeezes things in a quadrupolar pattern, shortens one arm and lengthens the other, and then shortens the other arm and lengthens the other in a periodic way. But of course, anything that rumbles along makes the arms vibrate. So the ends of the arms, the cavity mirrors, are hung on a pendulum. The idea being that the ground is shaking, but of course, let's see, how can I do this? What's the right? Yeah, I have. That's right. Where's the pointer? Beautiful. Okay, so here I am shaking around like crazy up here, and the tip of the pointer, because I'm shaking at very high frequencies, the tip of the pointer is not responding. So if you build a suspension that has a natural oscillation frequency that's very low, say 1/10 of a hertz or 100th of a hertz, and then the ground drives it at 10 hertz, it doesn't respond very much. But that's not enough. If you build 2 pendula and you stack them on top of each other, you get even better isolation. Does anybody remember? What was that?
I love that we have that.
So what?
I love that we build.
Yeah, we build. I'm deeply involved in building pendula. The minute we'll talk about suspension wires for the mirrors, that's also something I've been a real contributor to. Yeah, so does anybody remember, if you drive a pendulum above its natural frequency, how does the amplitude scale with the driving frequency? The amplitude goes like 1 over f, it turns out, in Lorentzian. So the power goes like f to the -2. So if you stack 2 pendula on top of each other, you get an f to the -2 reduction from the first stage times an f to the -2 reduction from the second stage. And then if you stack a third one and a fourth one, you end up with an f to the -8 seismic wall, we call it, because we think of climbing up the wall as you go to low frequency. But you get f to the -8 suppression of low frequency noise. And that's what LIGO does. The control system for these pendula is ridiculous. So now you can imagine you have a pendulum which has an exceptionally low oscillation frequency, right? It's a very low oscillation frequency. And it's stacked on top of another one with a low oscillation frequency, and it's stacked on another one with a low oscillation frequency, and another one. Okay, so has anybody ridden in a Buick? Maybe this is an American example. A Buick, right? It's like the old folks' car. It's the big 1970s boat. Nice, soft ride, right? Has anybody tried to take a mountain road with sharp corners in a Buick? That's horrible. The soft ride is directly correlated with hard to control. Okay, LIGO has just built the softest suspension ever, and now wants to lock, right? Have a resonant cavity for a laser, so it needs to keep the cavity arm length within, a fraction of a wavelength stably over hours. So you're driving a Buick and you're trying to really thread the needle on that mountain road. So this is a huge challenge. But in the course of this, there's a lot of mechanical modes in the suspension. There's not just the back and forth mode. There's torsional modes. There's bouncing up and down modes. And in particular, some of the bounce modes have ridiculously high quality factors. The pendulum just doesn't dissipate bouncing up and down motion. So in fact, I'm probably violating the rules here, but I don't think anybody's going to care. About 3 days ago, there was a, magnitude 5 earthquake at one of the sites. The interferometer fell out of lock because of one of these modes in the suspension of the mirrors, and it took a day or two to settle down because the quality factor of the mode is north of 1 million, and the frequency is at 1 hertz or whatever, so you can calculate what 1 million seconds.
Earthquake was in Montana.
Yeah, the earthquake was in Montana. Frickin' Montana. Okay, so anyway, the point is that not only is there sort of rumbling here, but there's things that look like they might be quasi-periodic, and many of them are actually exceptionally high quality. That is, over 4,096 seconds, they are really just sinusoids.
And you see those harmonics in the sensitivity curve, is that right?
We're getting there. Yeah. Okay. So we cannot see the gravitational wave in this data. We must do something. And what we do is actually part of, remember on Monday I made a big deal out of just so stories, right? Clever, convenient lies we tell ourselves about our data so that we can analyze it in a straightforward way. And so what we do here to process this data, to extract the gravitational wave, is going to be part of that just so story. And so, in particular, we're going to make a major assumption. We are going to assume that this data are what are called stationary. Stationary has a precise statistical definition. It means, where's the chalk? Yeah, maybe. Oh!
Wait for that to slip through.
Actually, it's called mistake. It means that if I examine... So let's pretend that the expected value of the data is always 0. So we'll just subtract off the mean. Stationary means the mean is not changing in time. It also means that if I look at the correlation between the data at some time and the data shifted, say by half an hour or something, that depends only, thanks Enrico, only on the time shift. Okay? So if I want to know, for example, if I had one of these perfectly coherent lines, if I want to know how strongly correlated it is with itself an hour from now, I don't need to know what time it is right now. I just need to know that the lag was an hour. Now, that is a major simplification. And it's not really quite true. Like, people go to work in the morning and they go home in the evening, except on Saturdays and Sundays, and then there's special holidays and national celebrations. Okay, so if you sense traffic, at some level this is wrong. right? In order to predict the correlation of traffic today with traffic next week, you have to know whether the national holiday is happening or not, and whether it's the Queen's birthday or not, okay? Right? But it's a good lie to tell yourself. And the reason it's a good lie to tell yourself is if you now think about taking samples of your data. Right? I have all these samples. And I will tell you the LIGO data is sampled. Yeah.
So the first two conditions that together is called stationarity and time.
This is called stationary. Yes. Sometimes, yeah, I'll just say stationary. The statisticians have a number of different senses depending on exactly how you define this. Which all have to do with the different ways you could do integration and the different ways an integral could be convergent. But for our purposes, yeah, this is called stationary. And the key point is the correlation function depends only on the lag.
And tau have a known distribution and not just be
A number?
value? Yeah.
That may be one of the weirder senses of stationary. I'm not actually sure. But for our purposes, it's a number. So this is like 3 seconds. You know, you're looking at the data correlated against itself, shifted by 3 seconds. So if you have a bunch of samples of this data at discrete times, and in LIGO, these times are happening at a sampling rate of about 16 kilohertz. It's just like a CD. You could really burn a CD of LIGO data. It's an audio frequency. Then if you imagine, let's call this whole big thing here the data vector. If you imagine forming a big covariance matrix, okay? So if I want to talk about my data, let's suppose that I want to imagine this data was, say, a multivariate Gaussian. Then what I need to know is its mean. Well, its mean is the 0 vector. And then I need a big covariance matrix, right, to describe how data point 7 varies with respect to data point 3, and data point 76 varies with respect to data point 0, and so on, okay? Then this covariance matrix, I'm going to write it out over here. Okay, right? It's the 0, 0 expected value, the 0, 1, 0, 2, the 1, 0, the 1, 1, the 1, 2, the 2, 0, the 2, 1, the 2, 2, etc. Right? Okay? And by our assumption, this is f of 0. This is f of delta t. If there were something here, it'd be f of 2 delta t. This is f of minus delta t. This is f of 0. This is f of delta t. This is f of minus 2 delta t, f of minus 1 delta t, f of 0. And so the pattern here is 0, 1, 2, 3, 4, minus 1, 0, 1, 2, 3, 4, minus 2, 1, 0, 1, 2, 3, 4. The rows of this matrix are cyclic. Okay? Because each row is just a ratchet one times like against each other. Okay? It turns out that cyclic matrices are easy to diagonalize. And the linear operation that diagonalizes this matrix this linear operation turns out to be the Fourier transform. That statement in the continuous language is the awesomest named the Wiener-Kinshine theorem, which is the most awesomely named theorem ever. It says that the autocorrelation function of a stationary process and its power spectrum are Fourier transform pairs of each other. The thing on the diagonal here, S, is just the DFT of the autocorrelation function. So this data looks messy. It has a lot of lines. It has correlations from moment to moment because the suspensions are responding in a regular way to noise. But if we take its Fourier transform, then each frequency component is independent. That's what stationary means. Okay? If we take the Fourier transform of our data, we turn its covariance matrix into something that just runs down the diagonal. Now, each frequency component absolutely doesn't have the same amplitude of its typical fluctuations. Some are bigger than others. But they're statistically independent of each other. So if we want to analyze the data for real, it's better to do it in the frequency domain, because you can take each component piece by piece. If you do it in the time domain, you have to consider the fact that things are wildly correlated. Okay, so we can estimate the amplitude of the noise at each frequency component by just taking a whole bunch of Fourier transforms of little stretches. So if I take a Fourier transform of one stretch of the data, I get something. I can calculate the magnitude of the variation in each frequency bin. But that's like taking one sample from a distribution and asking, what's its typical value? It's a noisy estimator. But I have almost an hour, I have more than an hour of data. I have 4,096 seconds. So if I take little stretches, let's say a quarter of a second long each, Fourier transform each one, okay, and then compute the average value of the squares. So the average value of each component is 0 because the average value of the data is 0. But if I square each component first, then I'm calculating a variance. So this quantity is, roughly speaking, the average value of the variance of the LIGO data at each frequency. Okay, it's called a power spectral density. How many people have heard this story before? Okay, excellent. About half. That's good. All right, fantastic. And you can see all these sharp peaks are lines. If I use more than a quarter of a second worth of data, these would also be sharp peaks. If you think about it, if you have a quarter of a second of the data, the Heisenberg uncertainty principle says that you can only really detect things that are, with 4 hertz resolution. So down here below 100 hertz, the lines get pretty smeared out, but there are large lines. In fact, this one's, that's the US power grid at 60 hertz. Yeah.
So I don't know if this is statistically taboo or anything, but if the PSD is like the average value of the variance of each one of these kind of discrete frequency levels, why is it never plotted with some kind of stretch? Why do we always see it as a single line instead of some kind of band?
Okay. In fact, there should be a band. There's a lovely paper. Let's see. Now I've forgotten the. I think it's maybe Nelson Christensen. Do you remember, Ilya? Okay. So in fact, I've averaged together a bunch of things, and you're right. There is an uncertainty on that. Now, if we're talking about 16,000 things averaged together, the uncertainty is pretty tiny. If you only average 8 things together, then you do get a band. And people who do LIGO data analysis have looked at the possibility, we'll come here in a minute to how we would do this, of extending this to incorporate some uncertainty in the PSD. And I think, is it Nelson Christensen? It's Christian Rover's paper, that's right. The reference is Rover. Hang on. something like, I don't remember the time.
2012 around then.
Yeah. Which talks about how you could incorporate the uncertainty in this PSD. There's also a lovely paper by Tyson Littenberg, which I think, Ben, are you on that paper?
I think so.
Yeah, I think so. I think I might be on that paper too. Maybe I shouldn't say it's such a lovely paper. There's a Littenberg.
We're all working on it.
From 13 that talks about modeling uncertainties in the PSD when we do our analysis. So yeah, in this case, I have an hour of data. I've averaged together 16,000 segments. The error bars on this thing are, very, very tiny. Okay, so this tells us if we were in the frequency domain, what the amplitude of the variance would be for each of our frequencies. However, I just said I like 150914 because I want to work in the time domain because you can make pretty pictures of stuff chirping. So how do we reconcile those two things? It's called whitening the data. If I take the data into the frequency domain, the covariance matrix becomes diagonal with elements that are this on the diagonal. If I now divide each frequency by the square root of its variance, I have unitized it, right? Now every frequency is an independent N01 Gaussian. If I run that back through the Fourier transform, I get a bunch of independent N01 Gaussians in the time domain. The penalty that I have paid is because this thing is not flat, the signal that I'm looking for won't look quite like the raw signal from a gravitational wave. The signal now has been distorted. It has its frequencies around 100 hertz preserved relatively well, but if it has higher frequencies, they're suppressed, and if it has lower frequencies, they're really suppressed. I'm going to ignore that effect in what I'm doing, but we, of course, account for it in our real data analysis. Okay, so I'm going to whiten the data, and this is just copied from the LOST tutorial. And so I'm going to produce some white strain, and let's, I know when 150914 happens, so we don't have to look through the whole hour. Let's just look at a chunk. That is 0.25 seconds around 150914 with a little band helpfully placed at the right spot. And if you squint closely at the band, you could imagine you see a big up, a big down, another up, a down, an up, a down, an up, a down, an up, and then maybe, okay? You squint hard. Our algorithms don't have to squint hard. They actually use real waveforms and calculate the correlation of the real waveform with this data. But if you squint. But it's kind of noisy, right? There's a lot of high-frequency noise. And that's just saying the waveform that I'm looking for, if this is real, is pretty low frequency. It's like about 100 hertz, it turns out. And this data is sampled at 4 kilohertz. So what could we do? I mean, it'd be nice if we were looking at data that we don't need to sample more than a few hundred hertz in order to pick up frequencies of 100 hertz. So you might think, let's just throw away, let's say every 10th, just keep every 10th point. We'll throw out 9 out of 10, right? That's the natural solution. We'll just downsample this data. Can anybody guess why that might not be a good idea? Yeah.
Aliasing?
Yeah, aliasing is one thing. That wasn't what I was looking for, but you're right, that is aliasing. So what aliasing means is if you downsample data by just taking every nth point, you run the risk that there's something that sort of has a frequency that's pretty close to every nth point and gives you really weird features in your data, basically because you are beating your sampling frequency against that. What I was thinking of was, if you just pick every 10th point in here, you're throwing out so much data. The curve is actually not going to look any smoother. It's just going to look sparser. What we really want is a smoothing algorithm. So we don't want to downsample, we want to downfilter. Okay, so if you take this data, and there's lots of ways to do filters, but I just did one that uses one of my favorite statistical functions, which is an exponential roll-off. So if you do that, now you go back into the frequency domain, and you multiply this data by some filter that is flat at low frequencies, and then dies at high frequencies. right? And what will happen is down here at low frequencies, if you think about what the Fourier transform is doing, if you take a low frequency sinusoid, you're almost averaging together mini pieces, right? You're averaging together the nearby bins in order to calculate that frequency amplitude. So this is just a principled way. I mean, we could do something called a boxcar filter. We could literally just average 4 neighboring bins together, right, and plot that result. But a more principled way to do it is to go in the frequency domain, suppress all the high frequency stuff, and keep the low frequency stuff. And then originally you put it out at the same sample rate, but now you can downsample safely because there's no high frequency junk, and you've properly averaged over the nearby points. So if we do that, this is what the whitened low-pass filtered strain looks like. And now, this is really looking a lot like something that could be a gravitational wave. Okay, it certainly is an oscillatory thing. And now I'm only showing you Hanford, but if anybody read the 1509-14 paper, you will have seen that you can do the same thing to Livingston and get very close to the same data with a minus sign and a time shift. That's intended to convince people that this is a real gravitational wave. In fact, it wound up just confusing people. Yeah?
Are you able to write that kernel analytically or not?
Yeah. That kernel is 1 over 1 plus e to the f minus f naught over delta f.
What does this Fourier transform pair look like?
That's an interesting question. It is probably... a exponentially decaying thing at the order. No, it can't be an exponent. It's got to be a 1 over tau. Or maybe 1 over tau squared. It's going to look a bit Lorentzian. So it's probably a Lorentzian in time.
It's not wiggling.
There's probably some wiggles in it. I guess I shouldn't try to answer that in my head. I'm not exactly sure. Yeah. It's almost certainly not a causal filter. A causal filter is something you could imagine actually implementing in the time domain by following along with your data. Mechanical systems like Pendula are causal filters because you push on them and you look at the output, and the output has a different frequency spectrum than the input, but it only depends on the past history. This definitely depends in both directions on, the value at t depends on the past and the future, which is fine if you're just filtering data, but is a bit fishy if you're trying to build physical models of stuff. Okay, let's see. Okay. So at this point, we have a figure that looks somewhat like figure 1 in the detection paper, or I put this on, wrong paper. I put this on the syllabus, this paper, which I love. It's not a highly cited paper, it's never going to be, but the collaboration put it out, 4 or 5 months after the detection. A little bit. And it is the paper you want to read if you're not heavy duty into the physics of the generation of gravitational waves to understand how we get what we get out of our data. So the basic argument in this paper is to look at this figure, which is pretty similar to what we produce. This has been filtered in a different way. Again, if you ply me with alcohol or coffee over a lunch or dinner, I can tell you about why filtering it this way isn't such a good idea and all the problems it's caused for us, but I'm not going to talk about that right now. And basically counting zero crossings to estimate the period of the wave as a function of time, and use that to estimate the mass of the system, bound the compactness of the final object by looking at where the maximum frequency occurs, and say that this is consistent, at least with a black hole, by looking at how fast that decays from its maximum frequency. Okay, so we're going to go through a little bit of that now, and we're going to build a model that tries to respect the basic physics in this paper that you can then fit this data with Stan and see that in a little more sophisticated way than they do in this paper, the numbers are right. Okay? How many people read this paper before class? Sweet. Well done, Ilya. Zohar, did you have a question?
So, going back to the low-pass filter,
Yeah.
is the cutoff much higher than any expected signals that we would?
Because I know what's in it, I put the cutoff at like, I don't know, I think I put it at 500 hertz.
Okay, but in reality, we would put the cutoff at like...
In reality, we wouldn't. Yeah. I mean, in reality, we would either take our 16 kilohertz and use the whole data stream, or we put the cutoff at 4 kilohertz, or, somewhere where we would be driven in that decision is either we're conducting a limited search on the data. I'm only looking for binary black holes. Well, binary black holes have a maximum frequency, right? We think that there only could be maybe 3 solar masses. So, a 3 solar mass object in spiraling into a 3 solar mass object has a maximum frequency that's, somewhere around 500 hertz. So we wouldn't look up at, 5 kilohertz. Or we'd look at the whole data stream and just figure out from our PSD, somewhere up here in the kilohertz region, and we're losing sensitivity again. So at some point we can low pass filter and just roll everything off. In fact, you see here this rolls off just before 2 kilohertz because the data have been low passed at about 2048 kilohertz, or 2048 hertz. I mean.
So another question going along with that: why is the data so oversampled compared to what we would?
Well, it's not that oversampled. It's like a factor of 4. I mean, yeah, it's yeah.
So I think the sampling rate is not necessarily determined by this output channel. Like the control system needs to be sampled at much higher frequencies.
Yeah, there are channels that come out a lot higher than 16 kilohertz. Carl's right. But for gravitational waves of solar mass objects, right, a binary neutron star has a peak, maximum frequency that's somewhere in the 1.5 kilohertz range. So there's not much point in going above 16 kilohertz in sampling if that's what you think you're looking for. Yeah, is that okay? Okay. So let's talk about this paper a little bit, and I'd like to focus on this sequence of equations from equation 4, 5, 6, and 7. Equation 4 looks suspiciously like something that Cole might have put up on the board, except it's got a 2 in it, and some G's and C's and so forth. So I guess you did put the G's and C's in the end. So equation 4 is the lowest order calculation of the amplitude of a gravitational wave from a source with a quadrupole moment Q. A traceless process quadrupole moment in the way we discussed with Cole. Okay? How could we turn that into a gravitational waveform? Well, if you had a source where the emission of gravitational waves was an insignificant component of its total energy, you're done. The quadrupole moment Q of a binary has a frequency that's twice the orbital frequency of the binary. So, cosine of 2 pi ft plus phi is the gravitational waveform, and then it's got some amplitude. By the way, I should say about amplitude, the first thing you should notice is there's a distance in here. So unless we know the distance to the source, right, the amplitude here is basically arbitrary in this paper. You can calculate what the intrinsic luminosity of these sources is, but for our purposes, we're just going to treat the amplitude as some factor. Okay, we're not really going to learn a lot from it. If you have an emission of gravitational radiation, though, where the emission is a significant component of the energy of the system, it's not going to stay constant in time, right? Gravitational waves are going to carry away energy, the orbit's going to shrink, the frequency's then going to get higher, the gravitational waves are going to carry away more energy, the orbit's going to shrink, the frequency's going to get higher. Okay, that's a chirp. And that strangely matches what we see in our data. Right, if you look here, maybe there's a bump here, and then there's another bump there, and then there, but it looks like the frequency, certainly this might be low frequency, and then maybe there's higher frequency, and then really high frequency, and then nothing. Okay, so I don't know if people looked on Twitter, people were chirping for gravitational waves when the discovery came out, right? People were making their best impression. If we could figure out what the frequency was at each time, we'd have a pretty good model of that waveform. So all we need to do is formalize that process that I just described. We have an amplitude. Hij is the second time derivative of the quadrupole moment. That means we can calculate an emitted energy. Let's put a sphere at large r, integrate h squared over the sphere. The d squared and the radius of the sphere cancel each other out. That's good, so the total energy emitted doesn't depend on where we put the sphere to extract the energy. When you do that, you discover that the emitted luminosity, it follows this formula. And if you plug in the quadrupole moment of the source, what you will discover is that it depends on a quantity called the chirp mass. The chirp mass is, this relationship between the masses. I prefer to remember it as the chirp mass is a dimensionless quantity eta, which I'll define in a moment, times the total mass. Okay, it's not immediately obvious. I mean, of course, this has units of mass, but it's not immediately obvious how this scales with the total mass. And eta, which we call the symmetric mass ratio, goes like that. Okay. In particular, if the masses are equal, then eta, then this thing here in the end is slightly less than the total mass. Okay? Now, what we could do is do a really detailed general relativistic calculation and get corrections to the energy formula and also to the frequency of the orbit. Right? What we're saying is at any given moment, the gravitational waves are emitted at twice the orbital frequency, which is approximately Keplerian, but as you get into the strong field, it's no longer Keplerian, so it changes with corrections. And the emitted energy is not exactly dependent on the time derivative of the quadrupole moment. There are corrections to that as well from GR effects as you get into the strong field. But at lowest order, it's good enough to just use the Keplerian orbital frequency and this rate of energy emission. And if you do that, what you discover is equation 8. The gravitational wave frequency as a function of time is the simple function of the chirp mass times the time before a coalescence time. This formula predicts the frequency becomes infinite in finite time. And obviously that's wrong. Proper corrections fix that, okay? But the frequency sweeps upward in time all the way to infinity. Okay? Does everybody get the picture sort of how that's derived? If you want to do the real thing, you do corrections. The simplest thing is to first do corrections in V over C, which is this post-Newtonian expansion that people have been talking about. If you do that, you get expressions like this. X is a parameter which can be related to the gravitational wave phase. Here, this theta is that dimensionless combination of chirp mass and time before coalescence. Nu is the mass ratio, and you can go order by order and 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 keep going. Okay. It's a mess. I'm very thankful there's people who do this, but this is a lifetime's worth of work. But for our purposes, to just get an estimate of how fast the thing is, how heavy the system is, this will be good enough. So in this paper, what they did was they just looked at crossing times. Each crossing time is a half a period. So you take, 1 over 2 crossing time, and that gives you a frequency. And they plotted frequency to the minus 8/3 power versus time. That's the thing that should give you T minus Tc. So this should be linear in time. And the slope of that line is roughly the chirp mass. And the lines they've drawn on that plot are chirp mass of 30 and of 40. The point of this is very simple arguments about emission at the Keplerian frequency and the rate of energy loss give you a pretty good idea that you're talking about a few tens worth of solar masses of compact object. Okay, just from the rate at which the frequency is evolving. You can tell immediately, for example, that this couldn't be a neutron star. A neutron star would have many more cycles between 30 hertz and whenever it coalesces, because the frequency would evolve much slower because the total mass is lower. You can also tell that this couldn't be an intermediate mass black hole. First, by the fact that it goes up to several hundred hertz, and an intermediate mass black hole will have a coalescence frequency that's lower than that. And second, by the fact that this evolution is much too slow for an intermediate mass black hole. That waveform would not have so many wiggles in our band. Okay, so right away you can tell sort of what kind of source you're looking at. All right. Oh, and here I've plotted, so I put in some helpful units. Those numbers, 1100 comes from the G's and C's in the problem. 4.9 times 10 to the minus 6 is the number of seconds per solar mass. Sorry, that's the G's and C's. That's actually pi's. 1100 comes from the pi's. 4.9 times 10 to the minus 6. So about 5 microseconds per solar mass. Deirdre, that's the number you said you remember.
Yes, that's my number.
Right.
My unit.
It's a good number to remember. I plugged in some numbers and plotted versus time. This is how that chirping frequency would be evolving for 150914. So it hit 100 hertz, not long before the merger, maybe 100th of a second before the merger, and then very rapidly shoot right up. So let's talk about how we build a model that we could actually fit for this. Okay. We already talked a little bit. We said we were going to assume that the detector data was stationary, and we're going to whiten it in the time domain. That's one part of our model. But what would the waveform actually look like? Could I write whatever that is. Could I write that? I mean, I just wrote it. I know I can write it. Is that a good model for the waveform that we might be seeing in this data? It's not crazy, yeah.
Maybe a time-dependent phase.
Well, I mean, this is kind of a time-dependent phase, right? I mean, you actually could write this whole thing, as a big phi of t, and d phi dt is the instantaneous, the instantaneous 2 pi f. So I don't think we need to add a time varying phase. Okay, yeah, but yeah, what about amplitude? When I look at this data, which has just vanished from the screen, did I turn this off somehow? Did we lose the bulb?
Goes to sleep.
No promises. Can you actually unplug this for a second?
Yeah,
sure. Just in case of the falling asleep. It's the cable is.
It looks like it's turned off because when it's not the cable for
you get a blue screen, right? Yeah, and it's blinking red up there.
It's making a lot of noise.
Yeah,
You might have overheated.
Wow. Gravitational wave data analysis is hard. Okay, well, it's going to be a bit of a different lecture if this is. There we go. So, indeed, who said amplitude? You said amplitude. Very good. Yeah. Indeed, the amplitude of this wave is not constant. Right? It's small at low frequency, it gets bigger, and then it decays away. So we'll have to do something with the amplitude. All right, is there anything else? Does it really look like this wave?
We don't know what that looks like.
Does it really look like that wave, which no one can see now? Goes to infinite frequency. Remember, this thing blows up at infinite frequency. I don't think that's quite right. That's certainly not right from the physics, right? The black holes get close, and then, this whole thing was based on they're at a Keplerian orbital speed, and they radiate energy slowly and move to a new Keplerian orbit. At some point, that falls apart, right? There's the plunge. They take the plunge. There's a last orbit, and they go and merge, right? So maybe we want to modify this. In fact, it's kind of interesting what the maximum frequency is, right? Because it tells you another piece of information. In the rate at which the frequency evolves, we learned about the chirp mass. But in that innermost orbit, we also learn about the mass, right? So maybe we want to introduce an Fmax parameter. So the frequency goes up, and then rolls off. Okay, so we have amplitude corrections. I'll come to that in a minute. Actually, I should come to that now. So the frequency sweeps up to some maximum frequency. We don't know what it is. We'll fit it, right? That could be one of the parameters that we extract from this. And in fact, that's one of the parameters that's talked about in the basic physics paper in the section that I didn't focus on. Okay, so now let's talk about amplitudes. So if I have a constant amplitude for something like this, what I would have seen and this part is intended to be, constant amplitude at low frequency, the frequency goes up so everything gets closer together, then you hit an Fmax and you just continue forever as a sinusoid. So we have problems. The first problem is the one that you pointed out. The amplitude should be tiny here and get bigger. And the second one is that this wave certainly doesn't continue forever at some maximum frequency. So let's solve the growing problem first. So if you don't think about it for a second, you might imagine doing something like this. Like the amplitude in this wave, the far past, it's close to zero, but we don't have any real good data there anyway. Over this region, the amplitude only changes by a factor of a few. So why don't we just make a Taylor series, right? It starts at some amplitude and it grows. But then if you think for a little bit more, you realize gravity is generally scale-free, right? There's one scale in the problem, it's the mass, and that's it. So it might be better to make the amplitude be a power law. Sweet. It's much more likely that the amplitude follows a power law than it follows a linear relationship. And in fact, it does follow a power law. I actually don't remember. Daniel, do you remember what's the power in the time domain on the frequency? I know what it is in the frequency domain.
That's probably 5/3, just like.
Yeah, this is probably 5/3. That's embarrassing that I can't remember that. But anyway, so we'll put in a power law amplitude. That will handle. Oh, great. Okay. Well, anyway, I'll keep talking on the board, and then we'll switch over in a second. So we'll put in a power law, so the amplitude increases. Now, what about this high frequency bit?
Couldn't you just put an exponential cutoff in frequency rather than...
I love it. Yes. In fact, an exponential, well, actually, it's really an exponential in time. You may not know that. I don't know how versed you are in GR, but when the black holes merge, they form a black peanut. and it kind of ooshes its way down to a single spinning black hole. And that ooshing is quasi-normal modes. And so the natural thing to do would be to just put an exponentially damped sinusoid. In other words, you hit the maximum frequency and then you start damping with e to the minus t over tau for some tau. Okay?
So that means you prefer to cut off the frequency entirely rather than the amplitude as a function of frequency.
Well, I guess I'm doing a mix of both, right? I'm saying you have, this is like a base waveform, and then e to the minus t at f max over tau. So it's a combination of everything. The amplitude goes as a power of the frequency. This goes as t minus, right? This is the normal mode. And then, of course, if I just put this in, it does something bad for times before the coalescence. So I have to put in this or 1 if t is less than t at f max. And now what we've built is something that starts at small amplitude. It grows in amplitude as it grows in frequency. It reaches a peak frequency, and it rings down with a damped oscillation at that frequency.
Right, I think it's f to the 2/3, not f-thirds.
It's 2/3? Okay. All right. Awesome.
Is there any disadvantage in using something not smooth?
Yeah, there is. In fact, you'll see if you look closely at the stand code, I didn't use this thing. I used something that is like this right around the transition and then goes smoothly to 1 and 0 on both sides. In fact, it's the same as that. Okay. So I think we've got our model. Now, what we have built is a really bad in-spiral merger ring-down waveform. You hear the words IMR a lot in LIGO. IMR phenom P, IMR phenom D, IMR phenom C. We don't hear that one very much anymore. Et cetera, right? IMR stands for in-spiral merger ring-down. What we did was the frequency evolution gave us an in-spiraling phase. We said the merger just looks like the last cycle of that, which is a bad approximation, but if we talk to Deirdre, she could give us better. And then the ring down refers to this thing being exponentially damped as a normal mode. Okay. Our IMR is IMR phenom Z for, I don't know. Anyway, it's a bad waveform. We use better waveforms when we actually do the fit, but it's sufficient to extract the frequency evolution, which gives us the chirp mass, the maximum frequency, the place at which you go from this peak into the damped part, a very bad estimate of the damping time scale. Now I'm going to put this down and gesture. If you look at this data, there's sort of the maximum amplitude. There's one more cycle, maybe a second, and then it's done. That black peanut, unlike the suspension modes of LIGO, is a very soft oscillator. It has a quality factor that's, I think, 2. So you get, a couple cycles, and then you're down in the dumps. But we can get some kind of estimate of that damping factor. And we get an amplitude. And just to convince you that that's a reasonable thing, I chose some reasonable parameters in exactly that model and overplotted them with the data. And they're not perfect, but you can see that you get, reasonable peaked heights sort of decaying away. You get something that follows maybe this exponential damping curve. The phase of the peaks is a little bit off. I should phase shift it forward a little bit. Okay, but this is at least sensible for the data. And that comes from using a chirp mass of 30 solar masses and, a choice of this and that. Okay. And there's a stand program that if you initialize it with something like this guess, will go off and sample. I hope. I was playing with it right before lecture, before I pushed, so hopefully it's not broken. If it's broken, I'll fix it up and push it this afternoon so you can play with it later in the week.
So you just said you use it play with the phase, and you're saying making phase a function of time wouldn't do that?
Well, I'm saying making phase a function of time is redundant with making frequency a function of time. Yeah, phase modulation and FM are the same thing. Frequency is just the first derivative. So you have to think of the phase as a function of time. The frequency is just the first derivative of this function. So if you specify an arbitrary function as the first derivative of phase, the only thing that's left is the integration constant. And otherwise, it's the same. I could tell you phi of t is you just integrate this. Does that make sense? Why don't? Okay, yeah. Why don't we talk some more? Find me a lunch. We'll sit down and play with it. I don't think I want to do that on board. Yeah. Okay. So now I want to talk about I guess I just kind of went over what is our just so story. Our just so story is first the data are stationary. Second, there's an in-spiral merger and ring down that look like the features that I just described and follow characteristic scales with the mass of the system. How could we improve that in the remaining, let's say, 15 minutes of time? I want to take suggestions for how we could improve that. What big chunk of data is missing? I'm showing plots in blue. Where's the red? Right? There's no Livingston. This is just in Hanford. I just picked Hanford because H comes before L in the alphabet. We could just as well pick Livingston. Are people familiar with that terminology? By the way, we use it all the time in Ligo. Hanford means a site in Washington. Livingston means a site in Louisiana. We call them H and L after Hanford and Livingston. So I could say, well, this waveform appears in 2 detectors. What would I need to add to my model in order to do that? Time? Yeah, there would be a time shift, right? Because one is 3,000 kilometers from the other. 3,000 kilometers? No, it's longer than that. Yeah, anyway. One is across the United States from the other. Are there other things I need to add to the model? How about a phase shift? If you think about the quadrupolar pattern that everybody's familiar with, right? If it's following some cycle, this short, that long, this short, that long, and then I turn my detector, then I get the same frequency, I get the same exact time evolution, just 2 times this angle in phase, lagged, or, well, it depends on the polarization. We'll come to that in a minute. Okay, so I need to include a time shift and a phase shift. Could there be an amplitude shift? So we haven't talked about it at all, but these things come in 2 polarizations. If you think about the orthogonal degrees of freedom, if I've got a detector like this, it picks squishing and squeezing. If I've got a detector like that, it sees nothing. Right? If I squish and squeeze, both the arms, because they're at 45 degrees to vertical and horizontal, change by the same amount. So my detector picks up nothing. It's still sensitive to gravitational waves. It's not sensitive to gravitational waves in what we call the plus polarization, which squeeze vertically and horizontally. It's sensitive to gravitational waves in the cross polarization, which squeeze at 45 degrees to those axes. So there's actually 2 polarizations of wave in here. They are out of phase with respect to each other by a certain amount that depends on how you're looking at the source, whether it's circularly polarized or linearly polarized. Those terms mean things to people from electromagnetism. If it's edge on, it's linearly polarized. If it's face on, it's circularly polarized. That's the phase angle, if you like. So because Hanford and Livingston, they're on the Earth, right? So they have to be rotated a bit with respect to each other. In fact, we tried to build them as aligned as possible. That was done so that you could make plots somewhat like the figure we've been looking at, where you can really treat them as if they receive the same signal. But they're rotated by a bit, so you would need to account for the fact that the amplitude could be a little different in the 2 detectors. So we've got it, yeah.
And then, because of the curvature of the Earth, you also have the plane of the detectors being...
That's right. So that's another reason why the amplitude differs. And in fact, that's basically it. The arms, like I said, they're as aligned as they can be, given that you stuck them on the Earth, and it's curved by a certain amount across the United States. And that alignment is so small that when making plots like this, you don't have to care. But if you actually want to, deal with the data, you do. Okay, so we would add a phase, a relative phase between the two detectors. We'd add a relative time shift. We'd add an amplitude shift. And then we'd be pretty good to go. We'd have twice as much data. That's a powerful consistency check, right? Because I'm telling you can get the masses from looking at Hanford. And I didn't say we added a mass shift, right? So you could get the masses from Hanford and the masses from Livingston independently, and you could check that they agree. And if they don't agree, well, then that's not a gravitational wave, it's something else. That's part of how our searches actually work. They find things in each detector independently and then demand that they have consistent masses and mass ratios and so on. Okay, so that's kind of if it's really a general relativity, compact binary inspiral, that's what we would do. What if it's not quite general relativity? What would happen? Like, maybe this power isn't quite right. You could change that power, I suppose. It turns out that dimensional analysis does a pretty good job of giving you these powers. If you write down Cole's formula, which didn't really use any GR, right? It just used masses and quadrupole moments, and it used G, I guess, so, gravity couples with a coupling constant G, but that's kind of constrained by, units. If you write that down, it turns out this power is fixed. But we could imagine that maybe the frequency evolution doesn't just depend on the chirp mass, and as it turns out, the mass ratio, in exactly the way that general relativity predicts. So maybe these numbers are different. Or if we're talking about the single frequency with time that where's that? Here. The equation we used, maybe these numbers are different, right? The G's and C's and chirp mass, anything with mass would go here, so you could put the total mass in or something. But that's not going to make very much difference because it means you just see it as a differently massed object. It would still look like GR. But if these numbers were different, and you had the next power in the sequence, right, then what you'd be doing is you'd be messing with these coefficients. We do look for that in LIGO. Our tests of GR change these coefficients. They treat them as undetermined parameters and try to estimate them and ask if they're consistent. Once you've measured the first two, the mass and the mass ratio, everything else is predicted in GR. Does it match? Can anybody estimate or think about how sensitive we might be to those sorts of deviations in this signal? How would you go about that? So you make up a new waveform model, right? We could even make it up here, right? You make up a new waveform model. It makes a different blue curve here. It matches the data better or worse. Okay, I don't know. How would you quantify, or what kind of thing would you talk about if you were asking about the sensitivity? What I would do, and the way that we think about it, is I would count how many cycles this wave goes through from, some estimate of the sort of lower frequency of the detector, which is, let's say, 30 hertz in this instance. That's where the noise curve really is, reaching its bottom, up to merger. And if your model predicts 5 additional cycles, it's ruled out. If your model predicts a fraction of an additional cycle, then it's going to look just like this blue curve, and you're done. So, fundamentally, your model would be based on some statement about the way the energy is measured in the gravitational field is a bit different than GR. So the energy radiated is different, so the time evolution is different. There you go, etc. But in the end, you would just turn it into an accumulated number of cycles in band, and you'd ask how many is that. And if it's more than 1, it's pretty detectable. If it's less, much less than 1, you're dead. Okay. Does that make sense to everybody? Okay. So when you read papers about, testing modifications to GR and so on, hopefully, if they're good papers, they'll tell you an estimate of the number of accumulated cycles from their modification in the LIGO band, or at least give you a way to compute it. And that's how you could tell whether, we should spend our time looking or not. Okay. So far, we've just talked about modifications to our just so story, sort of on the waveform side, right? We're talking about maybe different theories. We're going to put additional detector data in, which means we need to care about polarizations and time shifts. What about modifications to our just so story for the data? Right? Our just so story for the data was it's stationary Gaussian noise. So we immediately took a Fourier transform. We estimated a PSD by looking at earlier data. We normalized everything to unit variance, and we're done. What else could be in the data? Glitches. Glitches is kind of a catch-all thing, but the detector pops and hisses and so on, just like an old record player. So yeah. Now, if you had a glitch, so glitches can actually look, they can sometimes look a bit like this ring down. Usually what happens is some component of the detector gets hit with a hammer, and all of these things are, roughly linear modes. So some component of the detector rings up and rings back down. Okay? So you could expand, you're not expanding really, you're expanding your waveform model, but you're not really expanding the physics, like of the compact binary. You're just saying H is this plus H glitch. Where that is, something that looks like an element of the detector ringing up and ringing down. We do that. There are searches that look for an arbitrary number of glitches plus waveforms in the data. The lingo you want to look at is a program called BaseWave, which actually tries to estimate the right number of glitches. Could be 0, could be more, and calculate the right waveform. What about, so I think,
Are there any astrophysical sources that could be providing some background
yeah, there are in principle. One astrophysical source is literally what we've already talked about, just a lot. So if you, instead of having a single binary black hole, had a superposition of binary black holes, you could get stochastic buzzing. Now, it turns out that the rate of binary black hole coalescences is too small for that in these frequency ranges. So the rate of coalescence is about 1 every 15 minutes in the universe. And you can see, if you look at this data, it only takes a fraction of a second to pass through the detector. So there's not more than one of these in the detector ever. Period. But in principle, you could have a low, a hum
Well, they're not
of background sources.
in the detector. Well, neutron stars are going to sweep through in 10 minutes, right?
They don't take 10 minutes from 30 hertz, but if we were, if you're talking about the next generation of detectors where the lower limit might be as low as 1 hertz, then there really could be multiple signals in the detector at the same time. I suppose if you push the neutron star rate up too, there could even be multiple signals from 10 or 20 hertz in this detector.
And those would combine linearly, right?
They combine linearly, but they're out of phase. So what you discover is that at any frequency, the expected H is 0, but there's a variance. So they actually just look very much like additional, you don't search for them quite that way, but they look very much like additional power in this PSD. Because, there's thousands and thousands and thousands of binaries at any given frequency. And so when you add them all up, on average they add to 0, but their variance is non-zero.
What about eccentric depth?
What about adding an eccentricity parameter? You could do that. It fits in somewhat of an awkward space in that it's hard, so it's not the first thing you would do. And it's also, so going between eccentricity of, say, 0.9 things look almost nothing like this, right? No emission, no emission, no emission, no emission, black. No emission, no emission, no emission, no emission, no emission, black. No emission. So people do what they call periodic burst searches. So you don't try to model it like this kind of waveform with an amplitude that is 0 almost all the time. You look for a burst and a burst and a burst and a burst with a period close to each other. Small eccentricity things don't look that different from this. So, you probably get a small bias on your parameters, but it's dirty little secret. We don't measure amplitudes well anyway. So really what you see, you don't typically see the frequency content. You just see the amplitude kind of modulating a little bit. And so, yeah. I think that's about all that I had in mind for adding to the waveforms. Are there other questions? Does this seem pretty clear to people? You look at the frequency evolution, you get the masses, and you're off to the races. Carl? Yeah. Oh, that's right. Yes. Yeah, no. So, yeah, if you put in spins do two things. First, spins change the frequency, and they change it in two ways. One is, of course, they have their own gravitational interactions, so they modify the energy of the orbit. Okay, if you like, spins can be a reservoir of angular momentum or an anti-reservoir, depending on how they're oriented. Also, if the spins are slightly misaligned, then the orbit precesses and wobbles. And that changes the frequency that you get out on long time scales, because the precession and wobbling is basically shifting this phase around back and forth. And spins change the amplitude of the signal, because we talked about polarization content before. Well, if the source is moving around on the sky and its angles, the polarization content is changing. So your detector is sensitive to a particular combination of polarizations. That fraction of the total is changing, and so the amplitude modulates as well. Yeah. So yes, thanks, Carl. That was a big omission, wasn't it? Yeah.
This one's a bit more esoteric, but simulations of mergers in scalar tensor theory, which have spontaneous scalarization.
Yeah.
Effects that look like a sudden change in the mass ratio.
Yep. I don't think we currently have a flagship search or any kind of real parameter estimation for that. It's a bit tricky, right? Because it's probably not going to happen with these black holes. It's a neutron star thing. One thing people have talked about looking for is either modeling that as something like this, except it just cuts off early. So, right, I said, this T of F max is dependent on the mass in these simple theories, right? It spirals all the way up until contact, if you like, for neutron stars. If you measure neutron star-like masses, but the signal cuts off before contact, because what's happening is the phase is jumped and you're not tracking it properly, then you could try to detect these sorts of things. It's hard. I think, estimates are all over the map, right? I don't know exactly which theory you prefer, but for many of them, the spontaneous scalarization happens late, meaning at several hundred hertz or above, and our sensitivities aren't so great there, and so, it's a tricky thing to measure. But yeah, that's absolutely something you could put in. Okay. Great. I will, during the coffee break, just check that this runs. And if it doesn't, I will fix it and then push the notebook, and you guys can play around with estimating masses and making